Welcome back to Learning as a Hobby, everybody. Today I'm going to go over Chapter 3 in Michael Spivak's book Calculus, my summary for Chapter 3, and then in another video I'll do the selected exercises for that chapter. Chapter 3, actually let me just show you in the book here. Chapter 3 is the first chapter in what he calls part 2. The book is broken up into a number of parts, and let me just show you. Part 2 is on foundations, and the first part of part 2 is chapter 3, and that's on functions. So that's the chapter that I'm going to give you my summary for in a minute. Chapter 3 begins with a quote by Richard Dedekind from his essay on the theory of numbers, in which he I believe he was the first person to derive or to construct, excuse me, to construct the real numbers by the method of Dedekind cuts, which is the way he constructs the real numbers in here. And he, like I said, Michael Spivak starts chapter 3 with a quote from this book. So let me just read that out to you. The statement is so frequently made that the differential calculus deals with continuous magnitude, and yet an explanation of this continuity is nowhere given. Even the most rigorous expositions of the differential calculus do not base their proofs upon continuity, but with more or less consciousness of the fact, they either appeal to geometric notions or those suggested by geometry, or depend upon theorems which are never established in a purely arithmetic manner. Among these, for example, belong the above-mentioned theorem, and a more careful investigation convinced me that this theorem, or any one equivalent to it, can be regarded in some way as a sufficient basis for infinitesimal analysis. It then only remained to discover its true. Sorry, the lighting is changing in here. It's making it hard to see this. It only remained to discover its true origin in the elements of arithmetic, and thus at the same time to secure a real definition of the essence of continuity. I succeeded November 24, 1858, and a few days afterward I communicated the results of my meditations to my dear friend Dedekind, with whom I had a long and lively discussion, Richard Dedekind. So that's how the chapter 3 begins, or maybe I should say that's how part 2 begins. Chapter 3 is the first chapter in part 2. So I'm going to give you guys my summary of chapter 3. And just as an aside, this book is worth giving a read through if you're interested about the construction of real numbers. Spivak does have in the one of the appendices at the back of the book the construction of the real numbers through Dedekind cuts. So we will go through that at some point in this book. Not in this video, obviously, but at some point we go through the book, we'll take a look at that appendix. So let me bring up my my notes for chapter 3. And as I said, the chapter 3 is on functions. And what he does in this chapter is basically it's mainly a philosophical discussion about the proper way to define the notion of a function. And he starts with the provisional definition here, which is excuse me, which is a definition I'm sure that everyone is familiar with from your algebra or pre-calculus course, and even in calculus courses at the level of Stewart, for example, the Stewart textbook, give more intuitive definition of function. That is the one that he gives here. So I'm sure everyone's probably familiar with this. So the provisional definition says a function is a rule which assigns to each of certain real numbers some other real number. And there are issues with this definition because there, for example, is this word rule, which is really too vague to be used as a formal definition. The set of numbers to which a function applies is called the domain. All right, so this is our tentative definition of a function. Like I said, it's insufficient in many ways, but it's a useful definition because it's, intuitive. And most people, once you start working with functions, the definition, you know what it means, especially when if you are used to graphing functions and things like that. Okay, he introduces function notation here. X is an element of the domain, and the function f associates to that element of the domain an output value or a y value, which we denote like this, f of x. F is the name of the function. And this, like I said, this symbol here stands for the value of the function f evaluated at x. In other words, it's the other real number that's associated to the input value x. Right, so that's called function notation. Again, I'm sure that if you're watching these videos, you have at least seen that before. Maybe you've forgotten what it means, but okay, and then this is usually a statement that people make in a algebra, calculus course, etc. Just for ease of writing things down. Unless the domain is explicitly restricted further, it is understood to consist of all numbers for which the definition makes sense. Just as an example, if we look at the squaring function, f of x equals x squared, this is the function that associates to every real number its square. So because every real number has a square, we would say that because we aren't writing any extra restrictions here, it's understood that the domain of this function is all real numbers. And similarly, if we look at another function, let's say 1 over x minus 1, this function is, the domain of this function is understood to be all real numbers that make sense as inputs in this function. So the domain of G will be all real numbers with the exception of 1. 1 is not allowed to be taken as an input because you get division by 0 if you plug 1 in for x. So the domain here is all real numbers except for 1. This is the union symbol, by the way, which means that you're just stitching these two intervals together. Okay. Let me just clear this off the board, and then I'll go down to the next page. Right, he defines some important classes of functions. Probably the easiest type of function to wrap our heads around is polynomial functions, which is why they're usually the first class of functions that you're introduced to in a math class. So f is a polynomial function if there are real numbers a0 through an such that the y-coordinate f of x is given by this formula, an x to the n plus an minus 1 x to the n minus 1 plus, all the way down to a2x squared plus a1x plus a0 for all real numbers x. And it's understood in this formula that an is not 0, the leading coefficient is not 0. That's the coefficient of the leading term. The leading term is the one that gives you the degree of the polynomial. In other words, it's the one with the highest power of x, right? So that the highest power of x is the degree of the polynomial. He also gives the definition for the class of rational functions, which are all functions whose y-coordinates are ratios of polynomials, where the polynomial in the denominator is not identically 0, right? And then he goes into how we construct. So he constructs a larger family of functions that you can get by building new functions out of old ones using some operations. So here he talks about the algebra of functions. So if you have two functions, f and g, you can build a new function out of them using these operations. You can take their sum, you can take their difference, you can take their product, and you still get a function if you use these definitions. So for any element in the domain, if we know what happens to the y values for the function, we know everything about the function. So that's why these definitions just talk about what the y coordinates are doing. So the function f plus g evaluated at x is calculated by taking the sum of the y coordinates of f and g evaluated at the input value respectively. So f plus g of x is equal to f of x plus g of x, and there's similar definitions for the difference and the product of two functions. The sum and product are commutative, but the difference is not commutative, and that's because of the properties of real numbers. So here, this is a sum of real numbers. So because real number addition is commutative, it forces this operation to be commutative, and same thing for products. But just like for real numbers, subtraction is not commutative, so this is not commutative either. Right, we can also take quotients of functions. You just have to be a little bit more careful about the domain. I should say, I forgot if I mentioned the domain here at all, but in order for these new functions to be defined, the domain has to be the intersection of the respective domains. And for the quotient, you also have to take into account, eliminate any values of x in A intersect B that make the denominator 0. That's just for the quotient because of the way we define the quotient of two functions. F divided by g of x is f of x over g of x. So if g of x is 0, then you get division by 0, which is not allowed, right? And also division is not commutative. And the last important operation here is composition. The domain for the composition of two functions is defined like this. So you need the value of x to be in the domain of g, and then also the output of g at x has to be in the domain of f. Okay, so this function is, oops. So this is called the composition of f with g. So it's read f composed of g of x, and we define the y coordinate to be this number. All right, so the input is x, the output is f evaluated at g of x, or in other words, you evaluate g at x first, and then you evaluate f at g of x afterward. Right? This is also not a commutative operation. Right, and we have some familiar algebraic rules for these operations on functions. For example, function addition is associative, so is function multiplication. Function addition is commutative, and sorry, did I say commutative for the? This is This is associativity. This is associativity. This is commutativity. Commutativity, associativity. So function addition and multiplication are both associative and commutative. Composition is not commutative, remember, but it is associative. Right, and we prove in the book he proves the associative law for addition. So I'll do that down here below as well. The other rules are proved in exactly an analogous manner, so I won't bother doing that. But you could try it for practice. It's like I said, it's very similar to the argument here. So if we want to prove that function addition is associative, first we allow x to be an arbitrary element in the domain of the sum, so meaning it has to come from the intersection of the three domains. And then we look at what happens to the y value. So if we add f plus g first and then add h, and we evaluate that at x, we get this by definition, f plus g of x plus h of x, and f plus g of x is defined to be this sum of real numbers. So f of x plus g of x, we add first and then add h of x. And because this is a sum of real numbers and real numbers are associative, addition of real numbers is associative, we can move the parentheses to get this. And then this part is equal to this, g plus h of x. And then finally, this whole thing by definition is equal to f plus g plus h in parentheses of x. All right, so that shows that for any input value, it doesn't matter if you define the sum of those three functions as f plus g first, then h, or you take g plus h and then add f to it. So this is an associative operation. All right, and we're almost at the end here. In order to give the formal definition of a function, we need to have a formal definition of ordered pairs, because functions are defined in terms of sets of ordered pairs. And he does this in the appendix to chapter 3. There are no exercises for this appendix, but we need this definition for the definition of function. So I'll just go through this. There's one theorem in the appendix that's proved and one definition. So the definition of the ordered pair A comma B is given in terms of the set. So the ordered pair AB is the set containing the set, the singleton set containing A, comma, the set containing A and B. All right, and with that definition, we can prove this theorem that A comma B is equal to C comma D, implies that the respective coordinates are equal, so A is C and B is D. Okay, so let's do the proof. This is a conditional statement, so we start by assuming the hypothesis, let A comma B equal C comma D. Then that means that these two sets are equal to each other, right? Because this is equal to that, this is equal to that. Then if you look at the intersection of these two sets and these two sets, we get, so from the first two, if you take the intersection, you get the singleton set containing A, and if you take the intersection of the second two sets, you get the singleton set C. And since both of these are the unique element of those sets that are the intersection of the two, then this has to be equal to that, which means that the elements are equal. So A equals C. And then we just have to show that B is equal to D, and he does that in two parts. Case one is we assume that A is equal to B. If that's true, then this is equal to this, because the set AB is the set AA, which is just the set containing A. And since we already have that in here, this set would just, you could write it more simply like this. It's just the set containing the set, singleton set containing A. And because of our hypothesis, we know that the two ordered pairs are equal. That means that this set is equal to that set, which means that this has to be equal to that. And in order for that to be true, D has to be equal to A. And we know already that from assumption that A is equal to B. So D is equal to B, and that's what we wanted to show. All right, so that's case one. Case two is where A is not equal to B. So if A is not equal to B, then B is not an element of this singleton set, which means that B has to be an element of this set, the set containing A and D. And that means that B is either equal to the element A or it's equal to the element D, but we know that B is not A by our assumption here. So that means that B has to be equal to D, and that proves the theorem. Okay, and then the last thing that he ends with here is the formal definition for function. So here it is. A function is a collection of ordered pairs of numbers with the following property. If the ordered pair AB is in the function f, then and AC is in the function f, then B has to equal C. So in other words, the x coordinates are not repeated. So each of the elements of the domain are paired with one number in the range. Okay. And then we have a formal definition of what the domain is. Then if f is a function, the domain of f is a set of all A for which there is some B such that A comma B is an f. This unique B is denoted by f of A, right? So that like we said, the function notation here, this stands for the y coordinate, right? It's the the real number that's associated to the input value a by the function. All right, so like I said, that the entire section here is basically just leading up to this definition. There, like I said, let me just stop the screen share for a second. There's a lot of philosophical discussion in this chapter that I didn't talk about in my summary, which is why you should read the actual chapter yourself, because he goes through the difficulties and of defining a function and why we end up with the definition that we do. So it's worth reading that yourself. It's too much for me to go through in a summary. So, but that's essentially the ideas that are in that section. So I'll be posting the exercises, the selected exercises for this section relatively soon, I hope. I'm kind of busy today, so I don't know if I'm going to have time to post another video today. Actually, I'm pretty sure I won't, because I have a number of things I got to do. But within the next few days, I should be posting these solutions to the selected exercises for chapter 3. All right, and then we got Schifrin coming up again, then Simmons and Taylor and Axler. So keep on the lookout for those. I'll see you guys in the next video. If you do like this content, please like and subscribe so YouTube knows to share these videos with like-minded people. And until the next video, keep learning, everybody.